Hey everyone. So the next section of our study of mechanics gets us into what is commonly referred to as projectile motion. All the motions that we've discussed up until this point have been in one dimension. And we discussed earlier that one dimension means that we're basically stuck on a line, that we can go this way or we can go that way, but all of this motion has to occur on one line. As a result, our frame of reference is pretty simple. We're basically just stuck on a number line, right? And we have a 0 point that we call our reference point, and then this direction is positive, and that direction is negative, and we only have two choices, so that's enough to account for it. But that's not what happens in the real world. For example, we did the lab last week or whatever it was, where you threw the volleyball up in the air, and it went up and it came back down. As also a part of that lab, we did the cart going up and down the ramp, which, although it was slanted, that was really one dimension because of where we put the motion detector. Putting the motion detector at the top of the ramp basically is measuring only motion that is occurring along that ramp. The fact that it's slanted doesn't mean anything to the motion detector, it's just measuring motion in front of it. But again, that's not how the real world works. Alright. There we go. Up on the screen is a video of my son, and when your dad is a physics teacher, these things happen, that you're playing with your toys and dad wants to record them so that he can use them in class as examples of things. So this is a toy set called Mater the Greater. If you are familiar with Cars, that is Mater. He's dressed up like a daredevil, Evel Knievel kind of guy. So in a little bit here, what we're going to see is, and it's in slow motion, so my son has Mater up at the top of the ramp. He's going to let him go, and in a little bit here, this is in slow motion, that time at the bottom is not representative. So Mater goes down the ramp, then goes up, and then comes back down again on the other side. So while this is happening, oh, hold on. Oh no. Oh, disappointing. All right. So I tried to freeze Mater in midair there. There he is. Okay. In this case here, Mater is under the influence of gravity. There's nothing underneath him, so gravity is the only thing affecting him. Just like the volleyball in the lab that we did. The one thing that's different, though, is that in addition to gravity, well, gravity is not affecting Mater in the same way as he's moving. Mater is moving to the left, but gravity is only affecting him straight down. As a result, he doesn't follow a straight up and down or a one-dimensional path. He ends up in two dimensions, where he's moving both horizontally and vertically at the same time. Now, the things that we use to describe projectile motion or describe motion in two dimensions don't change. We'll still discuss displacement, we'll still discuss velocity, we'll still discuss acceleration, but we have to have a way to address them in two dimensions. And that leads us to some of the subheadings here on the title page, especially this one about vector addition. And we'll talk about that a little bit later on. How do we address this idea? But first, some definitions. This section deals with projectile motion. Objects thrown or launched into the air whose behavior is subject to the effects of gravity are known as projectiles. So the volleyball in the lab that we did last week was a projectile. It was an object thrown or launched into the air whose behavior was subject to the effects of gravity. However, projectile motion takes it one step further. Is the motion of objects moving in two dimensions under the influence of gravity. And so now when we talk about two dimensions, it's not just a straight line, it's not just either straight up and down or side to side, it's both. So instead of our frame of reference now being a number line with positive one way and negative the other way, now we have to account for positive and negative both horizontally and vertically. So now instead of our frame of reference being a number line, now we're dealing with a good old XY axis, a Cartesian coordinate system if you want to call it that way. All right? But some of the things, like I said, some of the concepts that we talked about earlier still apply. For example, projectile motion, objects moving in 2 dimensions under the influence of gravity, is free fall with an initial horizontal velocity. So the picture on the screen shows a real famous demonstration, and I'll give you an example of it in class as well, of these 2 objects, red object and yellow object. This apparatus up at the top here is a spring-loaded launcher, and it pushes the yellow ball horizontally off the edge of the device at the same exact time that it drops the red ball. So they become projectiles, they become objects under the influence of gravity at exactly the same time. But one of them is moving horizontally at the time, one of them is at rest. So their resulting motions are different, not because gravity is affecting them differently, but because what they were doing when they came under the effect of gravity was different. So the red object continues to fall just like it did before, right? And we can see here, this is accelerated motion. The spacing between the balls keeps getting successively bigger and bigger and bigger if those balls represent equal intervals of time. And we talked about that represents an accelerated motion just like an object that was dropped. The yellow object, though, maintains its horizontal motion while gravity is affecting it vertically. However, the horizontal motion does not affect the vertical motion. The fact that it is moving horizontally, the yellow ball that is, does not affect what is happening vertically. They occur simultaneously, but they are independent. Gravity is still accelerating that yellow ball in the downward direction, just like the red one. And as you can see from the picture, if we line the white lines being there as guidelines, each of these pictures lines up, the red ball and the yellow ball line up almost exactly. Just like when we showed the 9 pool ball in the picture on its up and down trip. This is only a down trip, but if we look at where the yellow ball ends up, where the red ball ends up at each successive time interval, they are exactly the same. Because gravity is affecting them vertically, exactly the same. The horizontal motion that was given to the yellow ball by the spring apparatus doesn't change what's happening vertically. The object will fall with an acceleration of 9.81 meters per second squared. Why? Because that's the acceleration of gravity here on Earth. That will cause it to fall vertically with that acceleration, causing it to get bigger and bigger and bigger and bigger successively in between each time interval. We can determine the velocity of this red one using our Suvat equations, right? Just like we did in the previous section. However, the yellow ball will continue with its horizontal motion. And if we neglect air resistance, which in this case, because we're dealing with something that is rather smooth on the surface, not a big mass to surface area ratio, we end up with the gravity being the only force or only thing that is affecting the motion of that object, but gravity affects things vertically. Gravity's pulling it this direction. There's nothing to change the horizontal motion. So, horizontally, the velocity is constant. It will maintain that horizontal motion as gravity is affecting it vertically. As a result, the combination of the horizontal motion continuing plus the vertical motion increasing because of gravity will, or how about the vertical motion being affected by gravity, will cause our objects moving in 2 dimensions to move in a parabolic path. It's a shape similar to the position time graph for an accelerating object, but here it's not that this is position and this is time, right? This is x position and this is y position. And we put the both of them together, we end up with a parabolic path. We're going to assume this to be the case for any motion that we deal with in this section, not worrying about air resistance, neglecting it at this point in time. We might come back to it, like I think I said earlier, we might come back to it qualitatively, but not quantitatively. Again, if we go back to this picture of Mater, right, he's going to move in a parabolic path from the time he leaves this ramp to the time he gets back to the other ramp. It may be a short, wide parabola, but it's still parabolic in nature. Now, that being said, we have to come up with a way to account for the fact that we have 2 different motions affecting the overall motion of that object. And as a result, we come up with, or mathematically, we look at the vector sum or the resultant vector of those vectors, or of those 2 motions. Here's a picture of an airplane, and the velocity of this airplane is 300 meters per second northwest. So what I'm going to do is I'm going to draw an arrow. I realize there's already an arrow on there, but I'm going to draw a different arrow, and of course I got to do this to get an arrow. Right here, and I'm going to make this arrow purple to look like this. All right, so that arrow represents the velocity of the plane, and like it says here, the velocity of that plane is 300 meters per second, and it's in the northeast direction. Because it's a vector, it needs direction, and so we can use that to describe the velocity of the plane. However, I think most of us would realize, kind of intuitively, that an object that's moving to the northeast is actually doing 2 things. An object moving to the northeast is moving both, is actually moving both north and east simultaneously. I guess let's put it down here. So the purple arrow is actually a combination of the red and the blue arrows. A motion north combined with a motion east, both happening at the same time, will produce a motion to the northeast. Okay? Now, how do they combine? Well, it's not as simple as addition. It's addition, but it's vector addition. Vectors don't combine in the same way that integers or scalars do because of the direction component. So we can't just say that this is 150 meters per second north and this is 150 meters per second east, and together they get 300 northeast. It doesn't work that way, all right? But we've kind of introduced this already with the displacement activity that we did earlier. If we can make the purple arrow the hypotenuse of a right triangle where the 2 sides are red and blue, that we can now mathematically determine what the purple arrow is. Or if we happen to know, right, if this is northeast, okay, that would imply that this angle here would be 45 degrees and this angle here would be 45 degrees. Knowing trig, hopefully you remember from geometry class, a 45, 45, 90 triangle has 2 sides that are exactly the same. but they are not exactly half of the hypotenuse, right? 1, 1, radical 2. So, while north and east would be the same in this picture, they aren't 150. We could use math and figure out what they are. I'm not going to do that now, but we could. So as long as we set up right triangles with our vectors, we can figure out what the resultant vector, or the vector sum, is. Or if we know the vector sum, we can work backwards and find the two sides of the triangle, right? So in this case, when we're dealing with vector sums or resultant vectors, we're going to use math concepts, right? Math concepts like the Pythagorean theorem, math concepts like sine being defined as opposite over hypotenuse, or cosine being adjacent over hypotenuse, or tangent being opposite over adjacent. We will use these trig identities when we are analyzing two-dimensional motion or two-dimensional measurement of motion to allow us to find vector sums. So if we took a look back at the yellow ball from the previous picture, and I realize this one isn't yellow anymore, the question of how fast is the ball going comes up. Well, that question is not as easily answered as just adding what is it doing horizontally and what is it doing vertically. We can't numerically add those numbers, but we can find a vector sum. So if we take, let's say, this picture right here, okay, if you notice in all of these pictures, okay, this object starts off traveling horizontally, and this is its horizontal velocity. But as it continues on the entire path, notice that that horizontal velocity, that vector representing the sideways motion, never changes because there's nothing to change it. The only thing affecting the motion of this object is gravity, and gravity is affecting things vertically, right? For instance, it starts off with the initial vertical velocity, or velocity on the y-axis, as 0. And then, if we continue looking at these vertical velocities, they keep getting larger and larger and larger. Why? Because gravity keeps accelerating in the vertical dimension. So I'm going to draw two arrows on this picture. Right? I'm going to draw first a yellow arrow to represent its horizontal velocity. Then I'm going to draw a red arrow to represent its vertical velocity at that moment in time. The resultant velocity is a combination of those two, but I can't just add them numerically together. Vector addition works in trigonometric identities, right? So here's what I'm going to do. I'm going to take this red one and move it over to where the yellow one ends. Simultaneously is the same as if one that we go in one order than the other order. And then that means that if I draw an arrow to represent the hypotenuse of this triangle, if I knew yellow and I knew red, I could find orange. Orange would be the instantaneous velocity. What is this ball doing right now? Well, to figure that out, we need to know what it's doing horizontally. What it's doing horizontally, what it's doing vertically, and then find the vector sum, or the resultant vector. Those two terms are synonymous. All right? We'll do this a lot more as we go along, but just keep in mind that as we're talking about the quantities that we use to measure the motion, velocity still means what is it doing now, but we have to take into account what it's both doing horizontally and vertically at the same time.